David Smith here with another flipped classroom math video. A few tips before we start. Remember that you can speed up or slow down the playback if that helps you follow along. You can also pause the video at any point to catch up with your notes or to try the problems before I explain. Lastly, you can turn on the captions and follow along with my words on the bottom of your screen. Today's topic, geometric sequences. So let's do a quick definition, look at a couple sequences, and then we'll go over some of the kinds of problems that you'll see in this lesson. So first off, this is a number sequence where each term is found by multiplying the previous term by some constant. And we call this constant the common ratio. So the numeric sequence, we added or subtracted a fixed number from the previous term. This time we're just multiplying by a fixed number. So check this out. Here's a sequence. See if you can tell me what the common ratio is. What do we do to this term to get that one, then to this to get that one, and so on. So if you checked it out, if you said multiply by 3 each time, guess what? You're right. Each term can be gotten by multiplying the last term by 3. Now check this one out. Tell me what the common ratio is for that term, or for that sequence. If you notice that this one is also 3, you're right. Okay, let's look at some formulae for our geometric sequences. Here's a couple definition things you've seen before. U1 is always going to be our first term. In this case now, R is our common ratio. Remember with arithmetic sequences, D was the common difference. Okay, so now we have a formula to find the general term. Remember, this is the explicit formula. You can go right to figuring out what whatever term of your sequence is. So for these things, un, the nth term, is just u1 times r to the n minus 1. So if we're looking at the fourth term, it's going to be r to the 3. So this is your go-to formula for finding the nth term. Now we want to define r in an interesting way here. R is the common ratio, and it's always going to be whatever un you're looking at, one term that's a little further along, that's one term further along divided by the previous one. So this might be the 9th term, this would be the 8th term. So if you always divide the term by the previous one, you'll get the common ratio, and that's going to be useful a little bit later. Okay, let's describe a sequence mathematically and answer some questions about it. Okay, so here's our sequence, 6, 8, 4, 2, dot, 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 on and on forever. So our first question here is, show that it's geometric. So here's the thing. We can use this equation, basically divide one term by another and do that repeatedly, and as long as we get the same common ratio, we're going to be in good shape. Now, by looking at this, you can kind of see the common ratio is 1/2. 16 times a half is 8, times a half is 4, times a half is 2. But let's do this a little bit more mathematically. So what I'm going to do is I'm just going to divide one term by the previous, and that should also be the next term by its previous, which should also be the next term by its previous. And we can see that all of these fractions are indeed equal, and they are 1/2, which is our common ratio. So this is a way to show mathematically with numbers that indeed this is a geometric sequence and it gives us our common ratio. So when you're asked to do that in the exercises, this is the kind of thing that they're looking for. Okay, now we need to find the general term formula. Like we need that formula, it's super handy, then we can calculate the 50th term or the 27th term or whatever we want. So what we're going to do is we're going to plug in what we know about this sequence into our general term formula, which I've put up there for us, and see what we get. So un, we'll bring that down. It's going to be u1, which is our 16, times r to the n minus 1. So that's going to be 1/2 to the n minus 1. And that's our general term formula, or our explicit formula. So you could find the 10th term. Oh, look at that. It's asking for the 10th term. So let's do that. u10 is going to be 16 times 1/2 to the 10th power. So I'm going to get out my calculator to do this. There's lots of different ways algebraically that you could do that. I'll be right back. do that. 16 times, now I'm going to put parentheses around 1/2 to the 10th. That's a pretty tiny little number. Equals, I get 0.15625. 0.1525. Now we could also write this as a fraction. Let's take a look, because this is really also 16 times 1 over 2 to the 10th. And so 2 to the 10th is 1024. So this is 16 times 1 over 1024, or 16 over 1024. And now we can reduce that down. This is 1/64. So now you're probably asking yourself, geez, David, which one do I do? If I don't give you a specific instruction, then either one of these answers is going to be correct. But if I say express your answer as a fraction, then you're going to have to do that. Okay, now let's do another type of problem. We set one up like this for the arithmetic sequence. It kind of works the same way, just different mathematics. A little more complicated. So we have k minus 1, k plus 2, and 3k are consecutive terms in a geometric sequence. So now we need to find k. So the problem setup step, I'm going to ask you to pause that right now. What equation are you going to be able to write using the concept of a common ratio? Okay, now if you realized that this divided by that has to be the same as this divided by that, you're right, because the common ratio is that way. So if we divide k plus 2 over k minus 1, that's the common ratio. Okay? Now 3k over k plus 2 is also the common ratio. So these two fractions have to be equal to each other. So now it's just algebra. We're going to wind up with a quadratic here, so the solution is going to be a little bit more complicated, but it's essentially the same process. Okay, once you've set up your common ratio, you cross multiply these two fractions to get rid of the fractions. Way easier than finding common denominators. So I'm going to do the top binomial first. That's going to give us k squared plus 4k. I keep wanting to write x. K squared plus 4k plus 4. And that's going to equal the second cross product. So that's going to be 3k times k, 3k squared minus 3k. Okay. So now I'm going to manipulate this equation, set one side equal to 0 so I can factor and solve. So I'm going to subtract 3k from both sides, or I'm going to subtract k squared from both sides. So that's going to make this one 2k squared. I'm going to subtract 4k from both sides. So that's going to make this minus 7k. So that took care of that, and I'm going to subtract 4 from both sides. So there's a 4. Now I have 0 on this side. So now I'm ready to factor and solve this quadratic. Okay, I'm going to go through this. This is assumed prior knowledge, but when you have a number besides 1 in front of your quadratic term, your squared term, you have to use this technique called splitting the middle term to perform the factorization. So the way we do that is we find out what our AC is. There's the A, there's the C. You multiply those out. So AC is going to be 2 times negative 4, or negative 8. Now we find two factors of AC of negative 8 that add up to the middle term. And those two factors are going to be negative 8 times 1. Negative 8 times 1, that's going to equal negative 8, and negative 8 plus 1 equals negative 7. So negative 8 and 1 are the two numbers that we split our middle term into. I'm going to bring this up here. So we have 0 equals 2k squared minus 8k plus 1k. And what's my last thing? Minus 4. So now this quadratic is ready to be fully factored. What we do is we take the GCF out of this and the GCF out of that, and that will get us almost all the way there. So there's a 2k in both of those. So that's going to be 2k times what's left, k k minus 4. Now, we notice we already have a k minus 4 over here, so we're in good shape. We can factor out a 1 from that. So this becomes 1 times k minus 4. So now we're ready to finish our factoring. It's these two, 2k plus 1 times this one. And here's a pro tip. If you've done this step right, the two parts in the parentheses should be the same. Okay, to finish this huge pile of algebra, now we can solve this equation for k. And when we have a binomial times a binomial, and they're different binomials, we end up with two solutions. So the way we do this is we remember the thing called the zero product property. If either of these two deals is 0, the whole thing is going to be 0. So what I do is I set this one equal to 0, 2k plus 1 equals 0, and I solve that. That gives us 2k equals negative 1, or k equals negative 1/2. So there's one solution. My second solution is found by setting k minus 4 equal to 0, and that gives us k equals 4. So now I have two solutions to this setup. We had these three terms that were expressed algebraically rather than actually term numbers. We did all our algebra, and we ended up with two solutions. So you could check this out with your common ratios if you wanted to do a plug-in step. Okay, this last example follows the same pattern that we did with the arithmetic sequences. So check this out. We know here, in this case, that u2 is negative 5, second term is negative 5, and the fifth term is 40. Okay? Now, this one is asking us straight up for the general term formula, or the explicit formula. So let's take a look at how these things would stack up. u2 is just u1 times r. Okay? The previous term times the ratio. u5 is going to be u1 times r to the n minus 1, which would be 5 minus 1, or 4. So all I'm doing here is I'm expressing my two terms that I actually know in terms of u1 and r. Now this is going to be nice and handy, because even though these aren't consecutive, I can divide them, and the answer I'm going to get is going to be some form of the common ratio. So check this out, see how this goes. So for our plug-in step, what you've got to remember is you're always dividing a later term by a previous term. So what we're going to do is we're going to divide this one, u1 times r to the fourth, over u1 times r. So this is the fifth term divided by the second term. Now let's just do the same thing. Fifth term is actually indeed 40, and the second term is negative 5. So these two ratios should be the same, because this actually is 40, and this actually is negative 5. So now we can do some canceling and simplify. First off, these cancel, the u1s go away. The r on the bottom is going to cancel, and this will go to r third. So this side is going to be r to the third. And then 40 divided by negative 5 is negative 8. Now how do we finish this? R to the third, we take the third root of both sides. So that's what number times itself 3 times gives us r. So r, the cubed root of 8, is negative 2. Okay? Because negative 2 times negative 2 is positive 4, times another negative 2 gives me negative 8. So don't let this negative under the sign mess you up, because when you have an odd number root, you can do that. If it was the square root of negative 8, we're done. We can't do that with real numbers. But when it's an odd number here, you can have negatives under the root symbol. Now we know r. We can figure out u1, and we can figure out our formula. We know u2. We don't know u1, but we do know this. u1 times r, which is negative 2, equals negative 5. Because that's how we get u2. We take u1 and we multiply it by r just one time. So now dividing through, u1 is going to equal 5 over 2. Negative 5 divided by negative 2 is just 5/2. So now we know our r, we know our u1, so now we can use our formula right there for un equals 5/2 times negative 2 to the n minus 1. And that is our general term formula, also called explicit formula. Now that you've finished, take a moment to write down any questions so you can bring them to our next class and get some help. You can also watch the video again to improve your understanding. If you enjoyed the video, please click the like button down below, and if you'd like to help me grow my YouTube channel, please click subscribe.